The PLC is the most critical component on a ride. Without it, the ride simply wouldn't work at all. But I wanted to take a deep dive into looking at just exactly how the PLC works, and I know that's why a lot of you are here today. So let's get right into it.
Now get ready. Here we go.
Ladies and gentlemen, welcome to the Ride Mechanic channel. How the heck are you doing today? This is your first time here. Make sure you like and subscribe and stay tuned for more content just like this, and check out some of the stuff I've already done if you're new here. Alright, today's episode I wanted to discuss the PLC. This is a very critical component in every single ride out there, whether it be digital or analog, and I wanted to talk about it. So the first thing, PLC. What does PLC stand for? PLC stands for P, programmable, L, logic, C, controller. So in the old days, these machines used to be done by relay logic. It was simple little relays clicking on and off one at a time that would connect a series of wires together and cause something to happen. Kind of like the light switch to your house. The light switch is kind of like that relay contact. When you turn it on, the light turns on. You're completing the circuit. The same thing with a relay. It's just a lot of little tiny, think of them like light switches on the inside, but they're controlled electronically. So when you say, I want to flick this relay on, it turns on, let's say, could turn on 2 light switches and turn off 2 other light switches that make the circuit work and function together. You string some relays together, and then you have a basic circuit. You can say, I want to energize this and make that light turn on, but this relay is energized over here. I don't want that light to turn on. So you put an interrupt in it to make sure that it prevents the light from working. The basic of a PLC is that, but it's done digitally. So in the beginning, there was a train, but no controller. So what the old Woodies, when they were first being built, would do is they would simply take the electricity and run it directly to a disconnect, which powered the lift motor. So the motors would simply just be on and constantly running, waiting for the next train to go on. And then the rides function with typically people operating handbrakes in the station, that when the train was ready to go and they made sure that the people were sitting and they weren't going to go anywhere, whatever safety belts or restraints that might have been used, they said okay, and then the person opened up a series of mechanical levers to open the brake in the track, and then that allowed that train to roll forward. It would go through, the train would go up the lift hill, it would go over, it would go through the circuit, and it would come back on the other side. As rides grew, as rides got older, so did the train, so did the track. Well, more trains on the track meant that there needed to be some sort of a safety. So now what would happen is that you would need multiple operators. You would need the operator in the station that was opening and closing the station brake to allow that train forward. But then you would now need another operator that was in charge of the brake towards the rear, where the other train was now coming in. But more operators also means more chances for mistakes. So mistakes can be made. One operator can think something's happened, release the brake too soon, and the 2 trains collide in the station. Never a good scenario. So then communication became very critical. They had to know when to release trains to go into certain areas, and they couldn't put 2 trains out on the track at the same time, otherwise they would collide out on the track. So these people became the first controllers of the ride. Needing more controllers, they needed more people, which means they needed more safety. As electronic components in the era started to shrink in size and cost, that means ride manufacturers started using them more to do small tasks around the ride. Now enters the new age of relay logic controllers. Push buttons, as you may know them, are simply just a little tiny circuit. You push them, the circuit turns on, you let go of them, the circuit turns off. This is also done in an electromechanical relay, and when you string these together, you have the first form of logic called binary. The binary logic is simply on is 1, off is 0. It's either a 1 or a 0. We can also refer to these signals as being low or off and high as on. Now when we want a command to happen, it has to go through a series of logical gates. It's really simple. If the gate is open, the logic can't pass. If the gate is closed, the logic can pass. Think of it in other terms as kind of like a drawbridge for that your car would drive over. If the drawbridge was up, the car can't go over. If the drawbridge is down and closed, it can go over. Now, the system that I just described is basically called relay logic. That's a series of gates opening and closing throughout a circuit that once they make the right pattern, the circuit closes, and whatever is on the other side, typically a booster motor, lift hill, light, whatever it might be, can function. So as they started relying more and more on these relay logic controllers to do more things for the rides, the size of the controller got bigger and bigger, which means the control systems got more complex, and they started adding more relays. 5 relays turned into 10, turned into 20, turned into 100, turned into 200. So these control systems were very big, very expensive, and there was miles and miles and miles of electric wire inside that could loosen, come undone, break, short out, possibly cause a fire, something along those lines, and just damage everything in there. Also very hard to troubleshoot. When you got 200 relays and one of them's not working right, they're really hard to troubleshoot. Enter the age of the computer processor. Computer processors are able to execute programs and calculations, essentially. We used a processor to write a program, and then gave the program another program to run, and now we have the programmable logic controller, or PLC for short. These PLCs use internal logic instead of relays and miles of wiring like its predecessor did. It's all contained in this neat little package mounted inside a control cabinet somewhere inside the ride. The PLC is essentially divided into 3 basic types of modules, of which I'll touch on some of them, but there's thousands of combinations out there, so I don't want to get too deep into any one particular thing. So we'll start with the processor. The processor is the thing that actually has the program loaded into it that you can manipulate your I/O into making real-world decisions. Next, we're going to have the inputs. The inputs is what you hook up to a device and say that when a sensor or something along the track turns on, it's going to put an input signal into this card, and then the PLC understands that that device out there has now turned on. And last, we have the output module. The output module is once the PLC has made its decision to activate something, the outputs are what is activated. So in this case, we could use an output from here to trigger another relay or a motor or something along those lines that makes something move out on the track. The 2 main types of outputs used are basically things called relay and solid state. Those are the 2 basic ones out there. Relays, these cards right here are relay driven. They are a set of mechanical contacts on the inside that close. The advantage to relay outputs is that they can carry a lot of current across them. Disadvantage is that the cycles, every time they open and close, put a lifespan on it, and then every so X amount of cycles on those relays on the internal side, they have to be replaced. The other one is a solid state type output, which is great because they have no lifespan. You can theoretically put millions and millions of cycles on them before the card might fail, meaning you could turn outputs on millions of times before the card fails. The downside is that they can't handle much current. So to put that into perspective, I can have a solid state output card turn on something like a flashlight bulb 1,000,000 times. But I can't have that same card turn on a light bulb overhead because it would burn the card out. I can have this relay card turn on the light bulb overhead, but I can only do it about 100,000 times before the card dies. For the input cards, there's basically 2 types. There's syncing and sourcing. Syncing basically means that the input is looking for 24 volts to come into it, and then sourcing is basically the negative side of that. If I was going to send 24 volts from the component and have essentially the negative come back to here, I think of it as reversed. So for this next type, we're just going to be talking about the processor. In this particular one, I could take the processor out of this rack. This is the actual processor itself right here. You can see the integrated circuits behind it, the chips that run it. That's all there is to these. There's not really a lot to them. So this is essentially your PLC, this little guy right here. The PLC operation is divided into 4 steps, which is where it basically read, execute, communicate, and write. How it moves from step to step every cycle is called a scan. The scan is actually the component that runs internally inside the processor, and depending on the processor, it could run anywhere from a couple of times per second to that scan can run up to thousands of times per second. So let's explain the scan cycle really quick. All right, the first scan reads the inputs. The first scan comes down through the processor and reads the inputs and starts to make note of all of the real world inputs that are turned on. Remember, these are coming from real world devices like push buttons and proximity sensors and things like that. The scan takes that information and then writes it in special slots inside the logic, and that puts it inside the logic code. So next, the scan solves the logic. The logic is typically stored inside the program vertically. It's one of the reasons why the logic is a lot of times referred to as a ladder. So it's a ladder logic style PLC. There are things like box logic and some other stuff out there, but for the most part, ladder logic, even though it's older, is still the most common thing out there to talk about. So in the program, the logic in that ladder is arranged to that the scan comes down and it now starts to solve each rung of the ladder. So as the scan comes down, it will start with ladder number 1. It will go through and it will determine what needs to happen on this ladder. If all the little gates of the logic are closed, then that ladder is active and it remembers that it can now get an output from that. And then as soon as it's done solving rung number 1, it goes down and solves rung number 2, and then 3, and then 4, and then 5. Most programs are hundreds and hundreds of rungs deep. So the logic has a long way to go. And then some programs, a lot of programs, use multiple ladders. Say once we get into this part, once we've gotten to this part, go ahead and jump to this other ladder and start solving it there. And there's ways to manipulate that logic inside the program to make it run faster. Once you're done with startup, you could have a whole ladder that's just designated as startup. But once you're done with that startup process, you could simply not do that ladder anymore and save the time. Next, the program runs an internal diagnostic to make sure that the processor and all the input and output cards are running and working properly and that there's no problems with them. Okay, next, the scan now starts going through and writing to all of the output modules. Remember when it scanned through originally and it took those inputs, and remember it solved logic, and I said if the ladder was true or if it was connected, it would then write to the output. Well, now it's writing to the output cards, and all those outputs are now being written into. If that ladder was a 1, it would write to that particular output. If it was a 0, it won't write to that output. By writing, I mean turn the output on or leave the output off. It can write to either one. In general, when it comes to the size of inputs and outputs, a lot of cards have 16 inputs or 16 outputs. That's not a universal standard, but it's kind of like a lot had that. So you'd see these little points on here going up to 16 on both sides. Newer modules on newer PLCs have also gotten smaller and smaller and smaller, and so have the outputs and inputs to them. Now a lot of the newer PLCs actually have inputs and outputs on the same cards. Those cards only have about 4 or 8 points on them, but the cards have much more capability than the older stuff had to it originally. Different types of processors out there. This is a remote processor that can be used somewhere. Basically, this guy fits into another rack or a smaller rack, something just like this, and then it's a modular system, so we can put the processor in to one side, and then, I'm sorry, they're upside down, and then keep adding more I/O expansion cards and just keep building them bigger and bigger and bigger and bigger. Now, one of the ways these things connect and we can see them is that we have a computer in the PLC room that is linked with the controller so we can see it. But we also run special programs on that computer because no one can actually touch and write code to that processor. The processors typically have some sort of a lockout on them. This is a cheaper processor that's not safety rated really, and then it's got a little switch. You could switch it into program mode or back to run mode depending on what you're doing. But on a regular ride, we can't just switch it into program mode or anything else while the ride is running. For that, the manufacturer installed a key on the front, and only certain people actually have the key to those processors, so they can't be switched in. The other thing is outside internet connection. Processors on rides typically are not allowed to have an outside internet connection. They are mechanically isolated from the internet, so there's not a threat of somebody hacking into it. Where one of those things is weakened is Wi-Fi signals that might encounter, but most of that stuff, the manufacturers, engineers, and everybody alike have turned all those things off, so you can't try to get into one of those controllers. So how do engineers work on the processors while the ride is in the commissioning phase, or maybe we're going through a special rebuild phase for it? The engineers can hook up to the processor with the ride running. Now keep in mind when engineers are doing this that the ride has no people on it. It's typically being operated by maintenance. So what they'll do is they'll switch it into a remote run mode so their computer can be active with the processor at the same time. And then the engineers have the ability to actually manipulate the code itself inside the processor. They can go in and take those little gates that are open and close, and they can go into a special file and tell that gate to shut. So those things are called forces. They can force an output on. So why would that be necessary? Well, let's say you're working on a ride and you're commissioning it, and you have a big long program, very complex, put in there to do something kind of mundane. But I'm the designer and I said, every time the train comes in and stops, I need to open the air gates, and then we're going to wait 2 minutes for the air gates to stay open, and then we're going to close the air gates. And then after that, we can dispatch the train. So it's an automatic program. When it comes in, it says, okay, open the air gates, let it sit for 2 minutes, then close the air gates. Well, when we're doing commissioning and testing, I don't want to wait for that time. I want to be able to just dispatch the ride again. Let's go, go, go. So how do I bypass part of the program? Well, I just go into that part of the program where it says open and close the air gates and wait for 2 minutes, and I just put something in front of the program to say, don't do that. Then that program doesn't execute. Well, the ride won't go to the next step until that program is done. So I go to that output where the program says I'm done, and I install a force into it, and I force it and say, you're done. And it says, okay. Forces can be digital, like in that case, that is inside the program. I forced it internally. There is no real-world output that happened from that force. I could also go into the real-world devices, these outputs here, and I could force them on. So for instance, if we were running the ride and I said, hey, what happens if I turn, let's say I put a bunch of booster motors on the track and I monitor their speed. And it's very critical that while the ride is running, that those booster motors don't run. So I want to test my program and see if it works. How do I do that? Do I just wait for the thing to fail? No, I can't wait for the thing to fail. That would take too long and it might not ever happen. So what I do is while the thing's running, I go into my output modules and I take one of the booster motors and I force the output on, which forces the booster motor to come on out there. And then what I look for is I look for my ride to fault out. And it says, yep, there's a booster motor running when it shouldn't be running. That's an example of forcing output. Forcing an input, do the same thing. Remember my air gates program that I was talking about? Well, maybe I don't even have the air gates. So I just need to dispatch a train, but I've got no air gates. But I've got two sensors that need to show the air gates are closed. Now, the simple way is to simply wire in those two sensors real quick and tape a washer to the head. The sensors are on now. Or I could just go into the input and tell it, you know what, those two sensors where they communicate, it's always on. Might not even have wires hooked up to it, but it's always on. This setup right here, I've got 16 inputs right here. With nothing hooked up, right now the processor could, if I force them, the processor might think I have all 16 inputs turned on. So that's how you force an input. The other thing that you could do inside of a processor is install an AFI. An AFI stands for always false information. So an AFI is essentially a force that we've installed permanently. Now, forces have their own special file where I go in and I could say, hey, my output for number 1 is a 0, and I simply just install a force and I put a 1 in there and say, you're a 1 now, and then that output turns on. Now, in the processor's logic, there is a section for forces installed, and it says, okay, I have a force installed, and that section goes active. Engineers inside the programs will look for things like forces installed and errors in the logic and other things, and they'll prevent the ride from running if they see that. So it's a housekeeping measure. You don't want to let something operate with forces installed, because one force means there's might be 2 forces, means there might be 3, and you don't know. So a lot of engineers like to guard against forces being left unattended inside the program. So what they do is let's take a float switch, for example. I have a ride that goes subterranean, means it goes underground. Well, I have a high water table and I have to look for flooding where it goes underground. So I'm going to install 3 float switches, 1, 2, 3, that if they ever turn on, that will activate the ride's safety system and shut the ride off, because it will say, like, we don't want the train going through there, it's flooded. So to be safe, to make sure that they're working, I use the normally open side and I watch one side, and then I use the normally closed side and I watch the other side. Well, during commissioning, they didn't want to do 3 float switches. They only wanted to install 1. So, without the other 2 working, I'm missing 2 signals to go back to there. So what I actually do is I go into the program and I install a bit of logic inside the ladder rung. I actually put a piece of logic in the ladder rung that is connected, and it's called an AFI, because that piece of logic will never ever change state. It is always closed, and it's always telling that input that it's on. The ladder rung is there. It has all the logic in front of it to make sure it works. I've essentially installed a digital jumper wire around it. Now, that is, when you're commissioning, a better option than leaving a force on, again, because you can monitor that force file, and if someone does something, you'll know about it at that point. If everything is critical inside the processor, Well, I'm sure you've all run a computer before and had the computer crash on you. Have you ever had a computer crash on you? It's not great. But the same question arises, like, how do we know when the processor crashes? Because it could just stop working, and it might do it in such a way where it keeps logic turned on. Maybe it keeps a break open, and the processor just crashes. More like a computer freeze up. You know, you ever do something where the little icon's turning, like it's trying to do something, but nothing's happening? You could get the processor to freeze and then keep something open, on, or running, which would be pretty catastrophic. The way to prevent this is using something called a watchdog. Now, there are lots of different watchdogs, and they work all kind of the same, but they all kind of work differently. The external watchdog is doing the same thing, except for now I'm using an output to trigger that external watchdog. I'm using a timer inside the program, and I'm sending that pulse out every, let's say, hundredth of a second. It's just sitting there. It looks like a flickering light. And I'm pulsing that thing at 1/100th of a second. And then I take my watchdog and I run that wire. I run the wire to the watchdog right there. And I set a little timer on it as well. And I say, hey, after 1/10th of a second, if you don't see your inputs go high or low after 1/10th of a second, fault. Goes okay. And typically the watchdog is what's holding the e-stop circuit open as well. One of the things the e-stops go through is the watchdog relay. So if that watchdog sees that PLC stop communicating, the watchdog drops the e-stop out, which drops all your peripheral motors, brakes, and everything else out of contention as well. So that's a safety circuit inside the PLC. At this point in the video, if you haven't already, please make sure you like and subscribe and give me some comments down there. Let me know if you've got any fun stories to add on to these. And then let me know if you want to see something for topics in the future too. I'm always up for new stuff. I've got a list of things that I'm making, but sometimes somebody says something and I'm like, oh yeah, let's do that one real quick. That really sounds like fun. I do enjoy getting that information. You guys come up with a lot of good ideas for videos, so let me know if you got them. You can also email me at ryantheriotmechanic@yahoo.com. Let's get back into the video. So when we talk about other forms of safety circuits, the relays would do a similar thing. They would branch out the logic and send the same exact signals down two different sides of relays, both doing the exact same thing. And the relays had to agree with each other, otherwise the circuit didn't work. Not very executable in relays because you're doing the same logic commands, kind of hard to do. So what they came up with was safety PLCs. That is, here's my main PLC, and then I will have a safety. I'll use this as an example because it's a smaller version. My safety PLC watches the main PLC. It's got a digital watchdog on the inside, and the two watchdogs communicate with each other. The main PLC watches the safety PLC, and the safety PLC watches the main PLC. The main PLC might have 200 points coming in and out of it. The safety PLC is just going to have a handful of critical points, e-stops, brake monitoring, some things like that, block control. And the safety PLC is basically just double checking everything it does. So the main PLC says, I'm going to let this train go, and the safety PLC and its program, running a completely separate program inside of it, has to agree, yeah, I'm good with you letting that train go, and then the main processor is allowed to let the train go. We could flash forward from that. That was a two-step system to they've taken a PLC that's the main PLC, and now they've duplicated the main PLC into two. Now you have an A and a B channel. So the A channel is your main, your B channel is your safety essentially. They're both identical programs. They're identical PLCs, but they have two different strains of logic on the inside to where the A PLC is pushing its entire memory out and it goes into the B PLC. And the B PLC does the same exact thing. It pushes its entire memory. It takes a photo of all of its I/O every tenth of a second, hundredth of a second, and pushes it to the main A PLC. And then what it does is that a program on the inside looks for those two images to match. So everything is put into mathematical code, and when I say all my I/O is in this configuration, then that produces a number. And then the upper PLC does the same thing, and it produces a number, and then it looks for those two numbers to match and say, okay, we both agree everything's happening. On top of both programs having to match constantly, a lot of times what they do is that the manufacturer will run power into the main PLC on top and give it a bunch of relays. Okay? And then when that relay says, I'm good, I'm going to close and let power through, that power comes out of that processor or out of that controller, and it comes to the next one and goes in this same exact card on the next one down. And then that PLC also has to say, I'm good. So your inputs are duplicated and your outputs have all the power running from the top PLC through the bottom PLC. Now, everything has to match. Both processors have to have the same image to work properly, and then they both have to agree that they close relay output card number 5, slot 7. They both have to close 5-7 and 5-7 in order to actually let the power go through out to the ride. So these things, the processors, the safeties, and everything else get incredibly complex very, very fast. So let's talk about remote I/O for a second. Again, I brought it up earlier, but here's the remote I/O that I did brought up. So why would you use remote I/O? Well, in order to get this to work, I have to have, let's say, all my input-output cards. Some rides have 5, 6, 7 huge racks of these things sitting in there, and I have to bring all that wiring back to this location. Well, if I have brakes and things like that working 1.5 miles away, trying to do these exact same processes, that's a lot to get on that wire to come all the way back to here to make speedy decisions. Not to mention you have to worry about feedback and everything else on these circuits that might produce false signals and give you erroneous faults and errors while the ride is running. So they put a box near what you're working on, and they start giving you remote I/O. Now all those signals and commands and everything else I need to do, I just take power from my main control cabinet 1 mile away, and I run whatever voltage I might need out to that cabinet, and then I now distribute it inside of that cabinet to these guys. And now these guys are taking the command from the PLC, which is typically run newer stuff on Ethernet. So it runs right through the Ethernet cable right into that guy. And now the processor in here communicates with the other processor in there. And now it can say, all right, I'm looking for all my inputs in this section. I'm looking for my outputs in this section. Most rides that use any type of drive system, whether it be LIM or LSM or anything like that, they have remote I/O all over the launch track. They're using them on everything. They're using them in the drive system to power the stators and stuff like that. They're using them externally to get train position on the sensors and things like what position track switches are in. All that is remote I/O because it's much easier to run 1 or 2 Ethernet cables all the way back to the system than it is to try to run hundreds of wires really far away. I know what a lot of you are thinking is like, well, weren't you just talking about the multiple processors and stuff being used together as a safety PLC? It's like a safety system. When I use 2 of those together, it's like a safety system. But these days, 50 years later, everything's much better now. Now safety PLCs are actually down to 1. We've gone away from 2 actually, and now we're down to 1. Allen Bradley makes the most of the safety PLCs out there, although if you go to any manufacturer out there, they have PLCs that are rated for safety. They're a very special rating. Typically they're a different color. There's lots of indicators that it is something special. But the interesting thing about a safety processor is that it does the exact same thing that the 2 processors did, but it uses a 3rd processor now. Everything is built into it. Even the I/O is different. It's very interesting. Now, to be fair, it's one of the systems I also have the least experience with. So if I get stuff wrong, you'll have to apologize now. But so in the processor, the actual internal chips that actually do the processing and hold the program, there's 3 of them in there. The processor is running 3 different programs all at the same time. They're safetied in. The processor is able to have things like safety signatures on the program to where the processor now knows if anybody has messed with the program at all. You can't sign into them, they're locked, they need a special code to unlock them. Well, so the processor has A, B, and C essentially on it. So it's able to run the same program 3 different times. It has its own internal and external watchdogs built into it already. So it knows if it has a problem. The I/O cards have the same exact thing inside of them. In fact, they also have little processors on the I/O card itself. And now we have safety rated I/O, which means on the old stuff you would have a relay, one little relay that closed that turned that output on. And now, to turn that output on, you have to have all 3 safety processors agree to turn that output on, and then it uses 2 gates, 1, 2, and then once 1, 2 gates agree on the inside of that output, it turns on the 3rd gate and actually allows the signal to go out. And all 3 of those gates internally are monitored. So if my 1, 2 close but the 3rd one doesn't, or 1 closes and 2 never does, then the I/O card itself knows that there is a problem. It's self-diagnosing, and it goes back to the controller and says, I have an I/O fault, and gives me the exact port that it faulted on. It might be card number 6, slot 1. And it says that I/O faulted for some reason. The I/O cards are addressed. They've got little diagnostics on the back where you typically can flip some dip switches, little tiny switches on the back side, and you address the card. So you put it back in, and you can take this card out and move it to a different rack somewhere else and plug it in there, and it still knows it's dealing with the same exact card, which is really cool because you could do troubleshooting stuff like that. You could program yourself a special card to do something, and then you can go around and plug it in somewhere and hook up your diagnostic to that one particular card as you take it around. All this stuff that these guys use produces what's called a safety rating. It's a newer thing. Newer control modules have safety ratings to them. For a SIL, and SIL stands for Safety Integrity Level. This stuff I had to get engineers to help me out with because it's not my normal information, right? For the SIL2, the system must function as required, right? 99% of the time or better. For the SIL3, must work 99.9% of the time or better. And there are SIL4 devices, but most of these are extremely costly, and they're used for supercritical processes. Things like a ride is actually not a supercritical process because it has lots of safeties already in it. There's lots of redundancies in it. There's people monitoring it. It's not a big deal. So actually most ride controllers are actually kept at an SIL 3, or older ones are like an SIL 2. Not so bad. But SIL 4 stuff is things like missile silos and nuclear reactors and things like that. Things that can really have a massive problem if something in that controller goes bad. So lots of life safety on those where SIL 4 come in. The SIL 4, why wouldn't engineers, want to use that for all the rides? Well, it's a happy medium on the costing. SIL 4 stuff costs a lot to maintain. There's a lot of stuff to do with those. So engineers typically it's just too expensive to use on a lot of rides, so they don't want to do it. So they save the manufacturer all sorts of money and just go to an SIL 3, which is still extremely, extremely safe. Everything is guaranteed to work 99.9% of the time. The other thing with a lot of these safety things is that if you increase the safety too far, then you decrease how much the thing will actually work. You basically get too much and the ride won't operate well. It's like there's too many things in the way, there's too many problems. I've been around and seen rides where they're like, we're going to add all these diagnostic tools and all this I/O, and we're going to know everything about it. It's going to be great. And all the thing did was fault like crazy, and nobody liked it because it was too complicated. There's the old phrase, they don't build them like they used to. It's like, well, think of a car from the 70s. How often did it break down? Right? It didn't break down that often. And now think of, what was it? It was measuring RPM, temperature, fuel, just the very basics. And if you think about it these days, we've got a modern car has sensors, hundreds and hundreds of sensors all over them, but now you can't troubleshoot that car. You need advanced diagnostics and computers to troubleshoot the car. Did we go too far? Engineers working every day to make the systems bigger and better and to make sure that they're done in such a way where they're not going to inhibit the operation and make the thing harder to work on, and they're still going to make them safety. They're still going to make them safer. So if you like riding these crazy rides, and I think we all do, you could really thank the modern PLC for doing everything that it should be doing every day, day in, day out. All right, I think that's about it for this video. I'm Ryan the Ride Mechanic. Make sure you like, subscribe, do all that stuff downstairs. It does help me out, and I do appreciate it. Let me know if you got any comments down there. You can always email me at ryantheridemechanic@yahoo.com. And just like a lot of things on rides, those air gates are monitored to know whether they are open or closed when they should be open or closed. So you need to stay off the air gates. Bye.